I hope you can see the slide. Okay. So welcome to class 10 of CH576 Statistical Mechanics. Okay. In the last class, we did this. We had talked about what is known as Gibbs paradox and other things. But I think you remember that I wrote the total wave function of if you have n non-interacting and indistinguishable, which I can also call identical particles or molecules, whatever you want to call it. Then the total wave function is given by this. And this Q is called, if it is a molecule, then it's called molecular partition function. We had worked in canonical ensemble, so we'll be working in canonical ensemble. But this relation, I said, okay, you take it for granted. I did not explain it much. So today I'll try to explain this relation. Why you divide this by n factorial. So first you assume that your particles are not indistinguishable, but they're distinguishable. But they're non-interacting, okay? There is no interaction between these particles or these molecules, but they're distinguishable. So what do you mean by distinguishable? I can color them, for example. I can tag them with colors, so I can distinguish one from the other. And indistinguishable means I cannot color them differently. I have to color them same. All are red, all are identical, all are blue. Okay. So like electrons, they're indistinguishable. All electrons are same, identical. So you cannot distinguish. So, but now I'm calling dealing with non-interacting but distinguishable objects or particles. If this is the case, then I can think of I have n number of such particles and they are arranged in different energy states. So the energy state of the whole system, for example, the total energy of the system, actually I can write it like as follows. Total energy of the system, I can write it as, say, EL. L is the particular state the system is. N number of particles, V is the volume of the total volume of the system. Of course, I can write like epsilon I A V plus epsilon J B V plus dot dot dot. You understand? Like epsilon K C V dot dot. Okay. So this A, B, C, they are like particle index. So I can color them. I can call this particle A. This is a particle number. Okay. Okay. If I have n particles, I'll have n such terms. I can have a situation, for example, I can have a situation. Okay, I, J, K are the energy levels. Okay, like energy levels. These are like energy levels. Particle energy levels. Okay. So
yes, sir.
There will be n such term, which is obvious, but you can have a situation that, okay, my particle A is in ith energy level, But I can also have a situation that my particle C is also in the ith energy level. So that will be another term in this sum, okay, in this expression. So it will be n such term. And the total partition function of the system, how would I write? Now the total partition function at that temperature. What will the answer? Of course, total, I use this notation capital Q. All are canonical partition function. And this is, now you just try, it is very important that you take a sum of this quantity, and this sum is over all possible energy arrangements, rather. Configurations, I can call it, isn't it? So I can have a situation in one of the configurations, my particle A is in energy state I. I can have another configuration where my particle is in energy state K. So I can have many such configurations. So I have to sum over all such possibilities. Okay, it is not the sum over particle level energy states. It is the sum over all possible arrangement, all possible configuration. Is this clear?
Yes, sir.
This is very important, and this is what is known as your canonical partition function, isn't it? Now, of course, if I expand this, I can write it like this, that okay, this is exponential of minus beta. You'll have epsilon I A epsilon J. I'm not writing other terms. And then this sum over all possible configurations or possible states, I can replace this as a sum over this particle level energy states, isn't it? You understand what I'm saying?
Yes, sir.
Essentially, it is equivalent of saying this. And since you have exponential, the function is exponential, the next step would be like this, because not only exponential, the particles are distinguishable. They're like A, B, C, D. They're of different colors. So what I can do, I can actually split this sum into product of sums, like 1 is over I, okay, another over is J, and then if I do this, I can do this because the particles are distinguishable. And this one you can write it as a product of, say, QA VT, QA VT, QC VT. Is this clear? So this will be a product of single particle or single molecule level partition function. Only if I can color these particles, I can distinguish these particles. Okay, and in general, I told you in the last class that this small q is called molecular partition function. In chemistry, chemists would call it, if you're dealing with molecules, then you can, this is in general, it is given by this. It's called molecular partition function. Okay, we are done.
Yes, sir.
We have done this, I think, briefly, but I am just repeating today. But now what happens if your particles cannot be colored separately, like differently rather? when you have this non-interacting, which basically means independent, but they are indistinguishable particles. Okay, then you cannot say, okay, I take particle A, particle B separately, particle C. I cannot do that, no? I go back to this because this I is a dummy variable, no? So I just from each configuration I see where my particle is. This red particle is sitting in one configuration. It is occupying epsilon 1. In other configuration, it is occupying epsilon 5. In other configuration, it is occupying epsilon 9, like this. So I just take those terms and add them and find the partition function for particle A. Is this clear? The first term. Similarly, I
Yes,
do it for particle B, particle C, and make a product of them. That is what your total partition function is. But if you cannot color these particles, you cannot distinguish, they're indistinguishable, then life becomes difficult. Okay, so I'll just illustrate this with some example. And the example is as follows, that I have two, like two in number, um, non-interacting fermions. Now fermions, like I can think of example is electron. Okay, so your partition function, it is 2vt. Now I have given you another information that okay, there are 4 energy levels available. These are available particle energy levels. And then I have one additional restriction. What is the additional restriction for fermion?
Only one particle occupies one state.
Yeah, additional restriction is that for a given epsilon I, occupation number is 0 or 1. So either the particle is there, or if it is there, then only one particle is there. It cannot be more than one. Okay, 0 means the particle is not there. Okay, so occupation number means the particle. Okay, so this in general, this if you write it down, you sum over, there are 4 states like ij. I put ij because now I have 2 particles, no, but I cannot put ab because they are indistinguishable. So actually there will be 16 terms in this sum. You can actually do it yourself. I'm not going to do it, but if you sit and try to realize that, you will see that there are 16 terms in the sum, but 4 terms are unacceptable. Why?
because both particles are in the same state
And these
in
4
those
terms are, you know, these 4 terms are like, one
I
term is
equal to
like 2
J.
particles are in epsilon 1. Second one is 2 particles is epsilon 2. Third term is 2 particles is epsilon 3. Fourth term is 2 particles is epsilon 4. So these are not acceptable, as these are fermions. Sorry. Okay. So how many terms I have now? I'm left with now 12 terms. Okay. Seem acceptable, isn't it? And can anyone tell me what are these
Yes.
12 terms? So let us write down first some of the terms. Of course, one possibility is that epsilon 1 and epsilon 2. Okay, two electrons. One is in epsilon 1, other one is epsilon 2. What is another possibility? Epsilon 1, epsilon 3. It's possibility. Another one is epsilon 1, epsilon 4. Any other? Yes, epsilon 2, epsilon 3. Epsilon 2 plus epsilon 4. Now epsilon 3 plus epsilon 4. Now these particles indistinguishable. They are all red in color, for example. I can distinguish. If we can distinguish them, then I can have another arrangement. What is that? I can exchange these two, isn't it? The one which is in
Yes.
epsilon 1,
Yes.
I can put in epsilon 2, and then the one which was in epsilon 2, I can put in epsilon 1. I'll get another term. So I should get this. Sorry. But is it acceptable? Similarly, I can do epsilon 3, epsilon 1, epsilon 4, epsilon 1. You understand what I'm saying? Epsilon 3, epsilon 2, epsilon 4, epsilon 2, epsilon 4, epsilon 3. But are they acceptable?
No, sir.
No, no, sir.
We cannot distinguish between them.
They are not acceptable. Why? Because they are all red in color, indistinguishable, as these particles are indistinguishable. Okay, so either you take this or this, 6 and 6. If you take both of them, then what is the problem? You count it twice, isn't it? So what is the outcome? Actually, you can take all the terms and then you can divide it by Is this clear? So 2 factorial is your n
Yes, sir.
factorial. N is 2. This is one very simple way of explaining, or actually, yeah, explaining this n factorial term. But what about bosons? You know bosons. You can say that bosons are different. So let us calculate bosons. Bosons. Now, bosons has no such restriction. Bosons are quantum particles which can be more than one in one particular energy state, particle state, isn't it? I can have n number of boson in particular energy state. So there is no restriction. No
They are still
restriction on occupation
indistinguished.
number, but they are still indistinguishable. But this is number, huh? So in general, let me explain one thing. For example, I have in general, I have n particle, okay? I have a collection of n particles, capital N particles. Okay, so I have collection of capital N particles. Now, so let me use another color. The energy of a state, capital E, how do you describe this? I can have a configuration like this, say epsilon 2, let me write down, I have just epsilon 10. I am dealing with bosons, for example. Can I have such configuration? How many terms are there? N particles, n terms. Is it clear?
Yes, sir.
Yes, sir.
Now this is for bosons I am doing, no? Why? Because what I do, I take one particle, put in epsilon 2, and rest n-1 particles I put in epsilon 10. It is acceptable for boson, isn't it?
Yes, sir.
It is not acceptable for fermion, but boson it is acceptable. So because this is fine. But again, this position 2 is not important, no? Where you plate is not important, because I cannot say which particle I put in, as particles are indistinguishable, no? So I do not know which particle I put in epsilon 2. I don't know, because I cannot color them, I cannot distinguish them. So if I write like this, energy of that state, particular state, I can always write like this. And this is also in the, isn't it? Same in terms are there. But can I distinguish between these two energy states?
No, sir.
It
No, sir.
represents the same state. Huh? It represents the same state. So how many, now I can change the position of epsilon 2. How many possibilities are there? N, no? Epsilon 2 can be located in any of the n positions.
Yes, sir.
Now I have given very simple examples with one. I give you a very simple example like this, that I put on every I have one particle. On each level I have one particle. This is another configuration I'm talking about, okay? Another arrangement. Now I cannot distinguish these particles. How many ways I can write down this? If
Just
one
one.
particle can be arranged in n places, then how many particles are there?
In power n.
N
No, just
factorial.
think about it. Think about it.
N factorial.
Yeah, it has to be n factorial, isn't it?
Yes, n factorial.
There are n factorial possible permutations. Okay. So then what is the answer? The answer is very much total wave function, sorry, not function, partition function. When I write, I should write it as q to the power n divided by this n factorial. Is this clear? Is this clear? Because otherwise, to restrict overcounting, otherwise I overcount, isn't it? If the particles are distinguishable, I
Yes,
don't
sir.
need to divide by n factorial, but the particles are indistinguishable, you have to divide by n factorial. Now I must say that this is also an approximation. This is true when your temperature is not too low. When your temperature is not too low, when the particle is not very light, and your density is low, then only it is applicable. Something like semi-classical, I would say. But this approximation will be using throughout in this course whenever you deal with quantum statistical mechanics, like particles which are indistinguishable. Basically they are quantum particles like electrons, or any bosonic particle like photons.
Hello,
Okay. Yes,
sir.
yes, yes.
Sir, this q raised by n factorial which you have used, this
Yeah.
is this is for non means
Non-interacting. Yes,
no,
yes.
not without restriction thing, no restriction.
No, 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 no. No restriction. No. It could be for fermion. Could be for bosons.
So the boson also the relation will be the same.
Same, same. It's divided by n factorial. Divided by n factorial. Okay. Because I'm saying it is epsilon 1, epsilon 2, epsilon 3. For bosons also it is like it is a good approximation that you divide by n factorial. It is for fermion you can see directly. Okay, for boson it is not so
But
straightforward to
but
see.
for boson also, suppose it occupies like epsilon, that earlier example that you showed, epsilon 10
Yes.
thing.
Yeah,
So
but the problem is that I can always think of that in epsilon 10 I have say in one sorry n minus 1 number of particles. I can also rearrange them, no? Say I also I say this is epsilon 10, but I say this is epsilon 10, I don't know what to call it, 1 prime, double prime, triple prime, like this. Okay, just to count. And then many ways I can write this epsilon 10, isn't it? In
yes,
that
sir.
expression.
Yes,
So
sir.
same argument will hold here, isn't it? You have a problem because you are seeing all are epsilon 10, but mentally if I think that is like epsilon 10 prime, epsilon 10 double prime, epsilon 10 triple prime, and then I can have an element like epsilon 10 prime plus epsilon 10 double prime plus epsilon 10 triple prime. But then I can also have arrangement like epsilon 10 double prime plus epsilon 10 prime plus epsilon 10 triple prime. You understand? The same thing you can do with epsilon 10. You have to do it mentally.
Yes, sir.
So yeah, but for fermion it is you can see because you are tagging, you're naming them like 1, 2, 3, 4, like energy levels, particle energy levels. Okay. So this is we're going to do throughout, and this is exactly what we did in the last class when you talked about Gibbs paradox, and you resolve the Gibbs paradox by assuming the particles are indistinguishable. So actually the particles are quantum in nature and they're indistinguishable, and you'll see that we'll go back and forth. Sometimes we'll treat these particles as classical, sometimes we'll treat them quantum mechanical, but the treatment we do is more like semi-classical treatment. Anyway, so now I come back to your ideal gas. We did this translational motion. Now this ideal gas is made of structureless point particles. So other than translational motion, what other kind of motion it can have, these particles? These are atomic, no?
Vibration.
These are monatomic. Vibration, how can you have? This is like so made of say helium gas, for example, at low density. They are like ideal gas, isn't it? Collection of n number of helium atoms. Other than their translational motion, they're moving. This is translational motion. What other motions it can have?
Then there is no other
No
motion
other.
possible.
Think. Because I have told that we are already in the quantum regime, so we have to do a little bit of quantum mechanics here. People who are coming from physics and
Are we
chemistry, they
talking
know.
about the spin degree of freedom?
No, I'm just talking about what are the motions possible. Electronic motion, isn't it? Electronic degree of freedom, of course. Nuclear degree of freedom. Inside the nucleus also you have motion. So basically energy state, you have transition energy, also you have electronic and nuclear energy, isn't it, for these particles? For the helium, these atoms could be in the singlet state or triplet state. You know this. These are different electronic states, isn't it? So
Yes,
you have
sir.
energy associated with these different electronic states. Similarly, if you go inside the nucleus of the helium atom, you'll see the energy levels in the nucleus. This is called nuclear states, isn't it? So at least you have to consider the electronic and, if possible, nuclear states of these atoms in order to make the story complete. Is it fine? Is it okay if I say like this?
Yes, sir.
Yes, sir.
Yeah. So let us now do this first. So the electronic partition function. Let me do this. Now, in the electronic state, we'll do at the single particle level. We'll just sum over these electronic states. And this electronic state, I can say this is the degeneracy of the electronic state times. Is this fine? Of course, this is degeneracy. For example, if I am dealing with helium atom, I have singlet state, which is degeneracy of the state is 1. Also, I have the next step state, which is triplet, which has degeneracy 3. Okay, you understand what I'm saying?
That is supposed to be W sub I, E sub I.
E sub I, I'm just E for electronic. Okay, just to understand. Okay.
Oh, okay, okay.
Small e, small e. And first, what you do? What you do that fix zero of energy should be fixed. Okay, say the lowest electronic state of that atom is your zero state. Energy is zero. I can fix it. No, that is my reference. I fix it. That is my reference. So I will measure any electronic energy state with respect to this state, which is zero energy state. Okay. So then, what will be the Q electronic? Obvious. I'll have a sum. The first term is going to be, the ground state is omega E1. The degeneracy ground state energy is 0. It is about 0. The next one is omega E2 e to the power of minus beta. Okay, now I can just, rather than calling it epsilon 2, I can always call it like epsilon 2 minus epsilon 1, isn't it? I can call it, and this is like delta epsilon 1 2. Of course, this is equal to, because your epsilon 1 is 0 by definition. We assume this is your 0 of energy. And of course, we'll have other higher terms. This is the, now, so for helium atom, I just give you some data. If I consider helium atom, then the fraction of, for the helium atom, the ground state is singlet, excited state is triplet, that you have done in quantum mechanics. In the lowest, this is term and symbol, I'll not do, but what will be the answer to this? The fraction of atoms, helium atoms rather, in the lowest triplet state. So the first excited state, actually, this is first excited state. What will be the answer? Can you, I'm calling it F2. What should I write here? Any suggestion? This is a fraction.
E
Omega
power
E2
minus
e raised to
beta
minus
energy by
beta delta.
Yeah, very good.
omega.
So it will be like omega E2 exponential of minus beta delta E12, if I want to call it like this, divided by the partition function essentially, isn't it? Sorry, this is, it is power of 0. I am writing it like this. Now, what is omega E2? Value of omega E2? 3.
3.
Now I'll give you some value of this. So if I'm working in at room temperature 300 Kelvin, and I can give you this energy gap is something like 770 in some unit. Okay. Then the fraction you can calculate. This fraction is very, very low. It is 10 to the power of minus 334, almost 0. Okay. Even if you go to very high temperature, say 3000 Kelvin, then also the value of F2 is very small. It is 10 to the power of minus, I think 33. Still small. Now what does it mean and what does it suggest? Can anyone tell me? What does it suggest? It suggests that, okay, a good approximation of this electronic partition function, I can write it as
Omega E1.
okay. Whatever delta E1 2. Yes. May not be required, isn't it? Depending on the system.
Yes, sir.
So for example, I can give you, I have some value, some fluorine atoms. This at temperature 200 Kelvin, this fraction is say 0.27. Then 400 Kelvin, this fraction becomes 0.105 as we increase the temperature. And at 2000 Kelvin, very high temperature, this fraction is 0.273. So maybe for this you need this, but most of the cases you don't need this. Okay, but we'll stick to this. This will take this. So we'll approximate this as in my okay. What about nuclear partition function? Nuclear partition function means you're going inside the nucleus. And the nuclear force, you know, they're holding the nucleus very tight. Actually, if you go inside the nucleus, you will see that these nuclear energy levels are separated by millions of electron volts. So they're highly separated. Then what should be the approximation? The good approximation would be your nuclear partition function
The
is
ground state.
just the ground state is 0, I assume. The degeneracy of that ground state, okay. Nuclear ground state is so this is a good approximation to your nuclear partition function. Okay. So this is your electronic partition function. for an atom. This is your nuclear partition function for an atom. Then ideal monatomic gas, what can I write? I know the ideal monatomic gas is going to be Q is Q trans, Q electronic, Q nuclear, which is this. And you remember what is the expression for Q translation?
2 pi mk.
It is done in the last class. This quantity also sometimes you read it like lambda cube. Okay, it's inverse of. So h square by twice by mkbt to the power half is called lambda cube. Okay. So this is the story for monatomic ideal gas. But nuclear partition function many times is omitted. So you can omit this actually, you can omit. People don't take it. Contribution is very small. Now, I go back to and then, so let us write down the Helmholtz free energy. You remember? Expression?
Minus kbt ln q.
So it is going to be minus kVt ln q trans, q electronic. Now q nuclear, I just don't take it, I told you, no? I just ignore. Sometimes it gives. This is how it is, isn't it? So it is going to be minus kVt. I can take that n common, no? Put it here. Let me write down properly. I hope you are following.
Yes, sir.
Minus
Yes, sir.
n kVt ln. Now let me tell you that ln, it is going to be q translation divided n factorial. So let me write down translation first. This is translation, but you have ln n factorial. But I know that ln n factorial, no, what I have here is minus of minus ln minus is not important, but you have ln of 1 by n factorial, which is equal to this minus ln n factorial, which is minus ln n is to be minus ln n plus n, isn't it? Is it clear? Because this is minus n, sorry, n ln n minus n, isn't it? This is how it is.
Yes. Yes.
Yes, sir.
So basically, if I arrange all this, I did in the last class, I think you'll get something like this. In this, remember this, that you'll get V E for this term, and this n you take out, and this ln n will come here, isn't it? This minus ln n. And then you have contribution coming from your vibrational, not vibration rather, sorry, electronic partition function. And you will see that this contribution is quite small. Small contribution. Of course, I can calculate thermodynamic internal energy. If you calculate, how do you calculate? E is, tell me, you remember the expression or you don't remember? Please tell me if you don't remember.
kBt square derivative of
Yes.
log Q.
Yeah, it is. Yeah, kVt square. You know that this term we did in the last class, you know, this is going to be nkVt. To do things properly, you will see that is nkVt, not plus, not minus, nkVt, because this is your expression for, I'm just putting the translational partition function, nkVt, but you'll have a factor of 3/2 coming, and then you'll have 1/t coming, isn't it? This is done in the last class. Plus, you'll have contribution coming from the electronics part, which we did not do in the last class. No. What is the contribution from the electronic part? Of course, let me write down n kb t square should be there. Sorry, this one is 2t square. Should be there. Then this is, you know, electronic partition function. You remember? Let me write down here again. Okay, you have to take a log of this. Remember, you have to take log of this, and then you have to
Yes.
differentiate that with respect to temperature. It's not, is it clear? That is exactly what you should do. But of course, so if you do this, you're going to get, so let me, so you know that ln q electronic, you know, ln of this whole thing, the one it is here. So I differentiate this with respect to temperature. What I'm going to get 1 over the whole thing, which is your electronic partition function. Let me write down. And then what you should do, you should differentiate this argument. No, this will be 0. Now you differentiate with respect to temperature, and you remember that beta is
1 by
1
kBt.
over kVt. So what I'm going to get this something like omega E2 was there. So minus delta E12 will come, exponential of minus beta delta E12 is there. And also because of this beta and temperature, that conversion, what I'm going to get minus 1 by kVt square here.
kBt square.
Okay, is this clear?
Yes, sir.
So, and if you rearrange everything nicely, you will see that the what I'm going to get, we're going to get 3/2 n kVt. This is done in the last class. Plus, you will have a term here which is n omega E2 delta E12. I don't need to care about n factorial, because ln n factorial, whenever you differentiate respect to temperature, that contribution is 0. Okay. Exponential of minus And you'll see that this has a very small contribution one can calculate, but it has some contribution. Very small, but some contribution it has. Okay. Now let us calculate something else. What next I can calculate? I can calculate entropy. Entropy is a very important thermodynamic function. How do I calculate entropy from canonical partition function? It is done in the class. Remember the expression?
K below Q
How many?
plus
Tell me.
K below Q plus KBT DDT of log Q.
AVT. This is the expression. I hope there is
Yes,
no.
sir.
So that you go back and check your thing, you will see that you will get it done in the last class in detail. I'm not going to do it again. Okay, there's no point. But then I'll have contribution coming from what? Coming from
Electronic
Electronic.
function.
electronic partition function. This you have done. Okay, this is, I hope I have not done any typo. Beta will be there, just check. Go and check. This is correct. I will just see the expression. I hope this is correct. Yes, I think it is correct. And this part I can call it S electronic. And this equation has a name. Anybody knows the name of this equation?
This is secure tetrode equation.
Yes, this is called Sackur tetrode equation. People who have taken CH408, they would know. They would know.
Yes, sir.
It is done, no?
Yes, sir. It is done, but that time it was not this much detailed.
Okay. So this is called Sackur tetrode equation. In the last class, we dealt with only this part, translational energy part, and we did other things. Okay.
Yes, sir.
So I can also calculate other quantities. For example, I can calculate the chemical potential. Sorry. This eraser gives me trouble sometimes. Okay. Okay. Now chemical potential is given by this expression. This minus kVt is the expression for chemical potential. Okay. Did I discuss this or I just did I? If I have not, okay, you can go and check yourself. Now what will be the
I
next
think we
term?
got it for microeconomics.
Yeah. So minus kVt del den n of, just look at it. This is your whatever, something like q to the power of n. In general, you have this, no? This is the structure. Your q is
Log of.
q turns into q electronic. And of course, you have a log of this. So what I have here is del n of n ln q minus ln n factorial, isn't it? Which is minus kVt del n then what will be the answer? The first term is going to be ln q. This one give you n by n minus ln n plus 1, and this 2 will cancel. So what I'm going to get? I'm going to get minus kVt ln by n. This is clear. This is not a very difficult thing to do.
Yes, sir.
So this is mu Tp. So I can write down now mu Tp. If I write explicitly, it is going to be minus kVt ln q electronic. You can also take nucleus if you want. Put q nucleus here. Nuclear. This is very straightforward. But we are dealing with ideal gas. Now, what is V by N? It's done in the last class. This is equal to.
KT by P.
So your expression now becomes I take that P part outside. And how can I interpret this term? This whole term. This is like no zero pressure term, isn't it? This kind of
Yes.
thing, you know.
It should
But
be
this,
Q electronic Q nuclear by N, correct?
by N, but I have taken the N here. Should it be there here as well?
Oh no, no. Yeah,
I
sorry.
took it here, no?
Yeah.
So now this is your chemical potential. And you know these things, these expressions from your thermodynamics. So the good thing, you can see this, the strength of statistical mechanics, that starting from a microscopic theory, you can arrive at all the thermodynamic quantities. The next thing would be to go beyond monatomic, and we'll do what is known as ideal diatomic gas. So basically it's an ideal gas, they're non-interacting these entities, but each entity is a diatomic gas. For example, I can think of nitrogen gas or bromine gas or oxygen gas like this, but they're ideal, they're not interacting. In reality they interact, but at low density, high, not so low temperature, you can think they're not interacting. So we'll do what is known as ideal. Ideal means non-interacting, no? The particles are non-interacting. Diatomic gas. And the model I'm going to use, this is called rigid rotor harmonic oscillator approximation. Okay. How many are there who did not have quantum mechanics? I think one person is there.
Yes, sir.
Yeah, so you just go and read. It's not very difficult, very basic level of quantum mechanics actually. So you can do the rigid rotor means it's like a pen like this, which is rigid, okay, which is rotating. This is rigid rotor, and harmonic oscillator, you know, classical, and you can do a quantum mechanics of that also. Okay, so we start with what is known as Born-Oppenheimer approximation. I think all the chemists would know this. So nuclei are fixed because very heavy. So nuclei, they provide a field, and this under this field these electrons are moving. So I can have what is known as internuclear potential energy. And I have a diatomic molecule, no? This is the distance r. So if I plot this, I know it will look something like this. And your zero of energy is here. Okay, and this is called R equilibrium, isn't it? This you know, all of you, I think you know from chemistry.
Yes, sir.
So your Hamiltonian, the total energy of the system, it is made of two. One is translational motion Hamiltonian, which is basically means that motion of the whole body, whole molecule moving. And then you have int mean internal. Okay, and this internal mean, we'll see what is this. This is for the relative coordinate. The coordinate is r, internuclear distance, isn't it? So if you can write down your Hamiltonian as sum of translational and internal Hamiltonian, relative coordinate Hamiltonian, you know that actually your energy is going to be also sum of translational energy if you solve the Schrodinger equation plus this internal energy, isn't it? Okay, and what is this translational partition function in this case for the diatomic? Can anyone tell me what is the translational partition function for the diatomic molecule? Very easy, because you know this is twice pi m kbt, isn't it? Yes, fine.
Yes, so will it be mu in this case?
No, in this case it will be m1 plus m2.
Oh, okay.
This is m1, this is m2. Because the translational motion of the whole body is the total mass.
Yes, sir.
So total mass. Okay. Okay. This is your total mass. And you put it there, and actually you can approximate this as a translational motion. Hamiltonian. Sorry, partition function. But u of r, how can I write u of r? You know that I can expand this around this equilibrium position, Re or R equilibrium. And then I'll have a Taylor expansion around this time, like R minus Re. You know this, the Taylor expansion essentially. Okay, what about this term? The first term?
Can we assume to be zero if that is the zero of energy?
Yes, it is. Sorry. Because you are at the equilibrium geometry, no? It is zero. So actually u of r becomes equal to, and then you can say that this part I can call it without the half thing, half is here. This is called K. And then this is given by something like u our equilibrium plus a by 2. I don't go beyond that term. If I assume this is harmonic, we'll do harmonic approximation. K is called force constant. And if you assume that it is harmonic oscillator, we stop there. This is harmonic, no?
Yes.
And these are anharmonic term neglected. Not just not included in our calculation, but in reality you can actually do this, but things will become very complicated. So let us do it with harmonic approximation. So now what is this rigid rotor simple harmonic oscillator approximation? It is getting clearer that your diatomic molecule has a spring which is Hookean spring, follows Hooke's law. It's a harmonic oscillator, but it is also rigid rotor in the sense it is kind of doesn't go with each other, but which basically means the bond length is fixed. Maybe you can assume this R equilibrium is your the bond length for the rigid rotor. When you talk about or we deal with the rotational motion of the molecule. So in general, I can write like this. That for the internal motion, your H internal is actually your this, and this is given by, I assume that rotation and vibration, these two parts can be decoupled. We can just write it as sum. And this is like a rigid rotor, Hamiltonian, a rotor where the bond length does not change, and this is like a simple, again, okay. Simple harmonic oscillator. Okay, and this is obvious that your energy is going to be rot viv is going to be E rot plus viv. And your this part of the partition function is going to be okay. Is this clear?
Yes, sir.
Uh, so let us consider vibration first. Okay. Now, what is the expression for E vibration? You know, people who don't know, just go and check. This is n plus half h nu. You know this, no? N is a quantum number which can have value like 0, 1, 2, 3. Vibration quantum number, isn't it?
Yes, sir.
Everybody knows, I guess.
Yes,
Yes,
sir.
sir.
Okay. And also, you know that the new frequency is 1 by twice pi k by mu whole to the power of half. Right. Mu is your reduced mass. This is called reduced mass. You know this I think. This is not a very difficult thing to do. And for a molecule, actually, you will see that it is around 1000 centimeter inverse. And the value of k is in the order of 10 to the power 5 to 10 to the power of 6 dynes per centimeter. Here's some information. You can check a book. It will tell you how it is done. Okay. So let us calculate the vibrational partition function first. Then do that calculation. Just wait for a minute. Today's class is mostly from the book by Mercury. See the book by Mercury. I'm sure it is done in CH408 people who took it, but I have to do it again. So your energy expression is given by, then what will be the expression for the vibrational partition function? Of course, function of temperature. And n varies from 0 to infinity in step of unity, isn't it? Now this one, you know, one half h nu that I can take out, no? This one I can take out. And then I'm left with this sum. Any idea how to carry out this sum?
Infinite geometric series.
You're right, infinite geometric series. So how many of you know infinite geometric series? I hope everybody knows, just but for the sake of doing, I'll do. So let us assume isn't it? So basically what I have here is this is like this, okay? You have to put n. So here you have a expression. So basically you have an expression. This is my y, sorry. Basically what I have here is 1 plus this is what you have here, isn't it?
Yes, sir.
And let x. So what I have here is 1 plus x square plus x cube. There is an infinite series because infinite number of terms in that series. So I can take this x common here. It will give me 1 plus x square like this, isn't it? And what is
Yes.
this?
Y.
This is actually x times y. This is basically tells you, take this on the other side. If I take y common, it is 1 minus x is equal to 1. This also tells you that y is equal to, so your q vibration now become, you had this, and then you have 1 by 1 minus x, which is, so this is the expression for your vibrational partition function using simple harmonic oscillator model. Is clear?
Yes, sir.
Yes, sir.
It is even not very difficult to derive actually if you can forget. Now if what happened that if temperature is high, temperature basically means that beta is 1 over kVt, so h nu by kVt is very small. So then I can actually approximate, I go back to the sum and I approximate this sum as integral. Like this. Why in the high temperature I can approximate? Because the high temperature means these energy levels will appear close to each other, isn't it?
Yes, sir.
Yeah, h nu by kVt small means these are the energy vibrational level, for example. Okay, so your kVt is like this, very large. So all these levels will look very close to each other. So then I can actually, this will appear like a band, isn't it? Because they are very close to each other. Because our measuring scale is kVt, that is my scale. So I can approximate this sum over these vibrational levels as an integral over this vibrational level. The variable is n, the vibrational quantum number. I then vary it from 0 to infinity as continuous variable. So okay, what are you going to get? What is the answer? This one is going to be, you know how to integrate this.
Yes, sir.
This is how, isn't it? No? What
Yes,
is the
sir.
answer?
1 over beta h nu into e power minus beta h nu by 2.
And this is going to be e to the power of minus infinity minus e to the power 0 divided by minus beta h nu, which will give you because 0 is 1, minus minus will cancel, this is 0. But again, this is nothing but because your beta is small, isn't it? Beta h nu is small, so it is over of minus. This will give you This is your vibrational partition function at high temperature. Is it clear?
Yes, sir.
Now I go back to the previous expression, the expression I derived. The one I derived using the sum, I can write it down. It was similarly in the limit. What will happen to this? I can expand this. Sorry. Because this is small, no? Exponential, I can expand. What I'm going
Yes,
to
sir.
get? 1
Beta
minus,
h nu. 1 plus beta h nu.
but this is equal to, again, this is, I can neglect. Huh? What I'm going to get is matching, no, with this.
Yes,
Just to
sir.
check. They're same, they're matching. So in the higher temp, when the temperature is high, this is going to be your expression. So next thing I can calculate is vibrational contribution to the internal energy. Okay. What will be the expression? The vibration. Can anyone tell me? You know, this is n
Kbt square
kbt n kbt square. I can write it like this, no?
d log q dt.
Okay, and this is also minus n. You remember this, no?
Yes,
Yes,
sir.
sir.
Yeah. Now, what is ln qv? Ln qv is going to be minus beta h nu by 2, the first term, minus ln of 1 minus t minus beta h nu, isn't it? Because qv vibration or v, whatever vibration or v, yeah. We did just now,
Yes, sir.
isn't it? So this is like this, okay? So now I take, I have 5 more minutes. What I'm going to get? I'm going to get minus h nu by 2 minus 1 over 1 minus, it is by minus beta h nu into 0 minus of and minus will cancel h nu. This is what I'm going to get, isn't it?
Yes, sir.
Yes, sir.
So it is going to be minus h nu by 2 minus h nu to the power minus beta h nu divided by 1 minus or minus beta h nu. But now I multiply this with minus 1 on both sides and multiply with n. So I'm going to get n h nu, like this is the expression, isn't it? Multiply it with minus n on both
Yes,
sides.
sir.
And this has to be your vibrational, isn't it? This has to be your vibrational energy. Okay. So let us assume, I call theta v, theta vibe, okay, theta v is fine, h nu by kv.
Yes, sir, disconnected.